In this video, we're going to take a look at a key topic known as the definite integral. And in order to do that, we're going to show how Riemann sums tie into this concept. And so to start, we're going to have a brief Riemann sum review. And what we're going to look at is the following example. We're going to look to approximate the area under this function, f of x equals x squared plus 1, on the interval 1 to 3, using left, right, and trapezoidal approximations with two equal subintervals. So on the left, I've marked off our interval that we will be working with, and I'm going to start by bringing your attention back to that statement about two equal subintervals. Well, if this interval goes from 1 to 3, so we think about its distance being 3 minus 1, and we split that into two equal pieces, each of them should be 1 wide. And that will represent the width for whatever shape we are going to be using for our Riemann sums. It also means that our two intervals in question will be the interval 1 to 2, and the other interval is 2 to 3. So for our left Riemann sum, which we will denote as R sub L, just recall that to calculate a left Riemann sum, we're going to work with rectangles. And so I'll go ahead and draw in the first rectangle, whose height will be determined by the function value on the left side of that interval. And I'll draw in the second rectangle on the interval 2 to 3, again, creating its height using the function value at f of 2 on the left side of the interval. And just recall the area of any rectangle is length times width. So the area for our first rectangle will be a width of 1 times a length or height of f of 1, the function value on the left. And our second rectangle will be a width of 1 times the function value at 2. And so getting these values, we'll have 1 times 1 squared plus 1, which is 2, plus 1 times 2 squared plus 1, which is 5, to give us a total sum area of 7. And notice from our drawing that this will have to be an underestimate. For this increasing function, our Riemann sum was based on always using lower values. And now we'll switch to the right Riemann sum, or Riemann sum sub R. So let's go back and draw in the rectangles for our right Riemann sum, now using the right side of any interval to determine the height for our rectangles. And notice these are really just going to cause extensions on the existing rectangles to create our right rectangles. The first rectangle has a width of 1 still, times the function value at 2, plus a width of 1 times the function value at 3. We already had that f of 2 was 5, and to get our f of 3, that's 3 squared plus 1, or 10, giving us a total sum area of 15 for the right Riemann sum. And again, just like on the first problem, we can judge whether this is an over or underestimate by recognizing that we were using higher function values throughout that approximation. So the right Riemann sum is indeed an overestimate. And finally, we'll calculate our trapezoidal sum over this interval, or Riemann sum sub t. Recall the area of a trapezoid is 1/2 the height times the sum of the two bases. So for our first trapezoid, we'll have 1/2 a height or width of 1. Our first base will be determined by our function value at 1, and our second base by a function value at 2. The second trapezoid will be 1/2 times 1 times the sum of f of 2 plus f of 3. And now we'll sub in the function values, which we've already calculated earlier in the problem. So the first trapezoid will be 1/2 times 1 times 2 plus 5, plus 1/2 times 1 times 5 plus f of 3, which was 10, to give us a total sum for the trapezoidal Riemann sum of 11. And we can go back quickly to the graph and draw in these trapezoids. And notice the trapezoids, because of the concavity of the graph, have a little piece that will be over the graph itself. So this approximation will be a tiny bit over the actual area we wanted to calculate. So here's the question to get us to our main concept. How close are these approximations to the true value of that area, and how can we make a better approximation? Well, notice the trapezoidal sum was definitely the closest that we were going to get to the exact area, but it was still a little bit over, and the only way to really improve is going to be with more shapes. Split this area into even more pieces using smaller intervals. Maybe use 4 subintervals, or 20, or 100. No matter what number you pick, we're now getting ourselves to the main idea, which is the definite integral. And a definite integral is defined as the exact area that is bounded between a function f of x and the x-axis. And this could change. It could be a function of time and the time axis. The main idea between some output function and the axis that represents your independent variable. And the notation for the definite integral is what you see below. This is read as the integral, which is that elongated s you see at the beginning, the integral from a to b, where a and b are our boundaries, for the function f of x with respect to x, or with respect to the x-axis. And the concept behind the definite integral and how it was developed is someone had the idea to think about a summation, there's our sum symbol, of a Riemann sum with n subintervals, and they thought, what would happen if we let that number of subintervals approach infinity, which could be accomplished by using the limit as that number of subintervals approaches infinity. Eventually, you wouldn't be able to tell where one shape started and the other one ended. You wouldn't be able to tell if it was an over or under estimate. It would look very much like what you see on the graph to the right, where we have taken our original problem, f of x equals x squared plus 1, and shaded in the exact area bounded between that graph, the x-axis, on the boundaries 1 to 3. And the notation for that area would be the integral from 1 to 3 of x squared plus 1 dx, or with respect to x. And now we'll get into some particulars about what exactly we're calculating and properties of this new notation. So what this represents to us, this definite integral, as we stated in the definition, this is the exact bounded area between a curve and the x-axis. Getting more into the concept of what this area is going to represent, think about the units for area being equal to the units for f of x times the units for x. Any two-dimensional shape, you get its area by multiplying the two dimensions. And the area that we end up calculating represents a net change in that new quantity that we have developed by multiplying those two dimensions. It's a net change in that quantity over the interval that we have set up. So for example, if f of x were given in miles per hour, so represented a velocity graph, and x were given in hours, then the definite integral, or the area under f of x, would represent a net change in the f of x units miles per hour times the x units hours, which would leave you with a net change in miles, which is a pretty big concept overall for this idea of the integral. And finally, the area can be positive if it is shaded in above the x-axis, it's representing a positive net change, or it can be negative if it is shaded in below the x-axis, representing a negative net change. Finally, we will end on properties of the definite integral, things that we are allowed to do with that notation. The first is the zero integral, which states that the integral from a to a, starting from one boundary and ending at the same boundary, for any function with respect to x, will equal 0. If you haven't moved along any interval, there is no area to calculate. The second property is the negation property, which states that the integral from b to a of f of x dx, where the boundaries are not in the order we started with, will be the same as the opposite of the integral from a to b, for f of x with respect to x. Basically, if you read in the opposite direction, you change the sign. The third property is multiplying by a constant. If you calculate the area from a to b for a constant k times f of x with respect to x, that is the same as the constant k times the integral from a to b for f of x dx. You can more or less move the constant multiplier outside of the integral. The fourth property is the decomposition property that states that for any value c between our boundaries a and b, if we calculate the integral from a to b for f of x dx, we can split that integral into the integral from a to c for f of x plus the integral from c to b for f of x with respect to x. And the idea is, if we have a bigger, more complicated area, we can break it into smaller parts to make the integration easier, as long as that c value lies between our original two boundaries. And finally, the addition-subtraction property for the definite integral states that if we take the integral from a to b for a function f of x plus or minus a second function g of x with respect to x, we can break this into two smaller problems, which would be the integral from a to b of f of x on its own, plus or minus, matching the sign of the original problem, the integral from a to b for the g of x function with respect to x. And that does it for the definition of what the definite integral represents, along with properties of this new definite integral notation. Please make sure that you familiarize yourself with both sets of concepts before moving more into the application and how we utilize the definite integral itself. Thank you for watching.